Hey ho. Okay. Hello. Good morning. Welcome to Physics with Keith. It is the first session of the autumn term. We're back. It's 10 o'clock in the morning, and I did toy with the idea of using Facebook Live, but it's still not quite as smooth as using YouTube Live. So we'll stick with this for now, and maybe we'll go back to it later. This is a live tutorial, and already I can see there's a bit of conversation going on the YouTube chat, which is wonderful. Just a little reminder, I mean the chat's public, so I don't think anyone's going to mind me showing this, but just a little reminder, if you want to chat with me while we're doing this live tutorial, share questions or answers or anything like that, the way you would do that is by using the chat box, which is on the right, in my window, it's on the right of the YouTube page. So you can go ahead and pop your chats in there, and I will be able to see them and respond to them in real time. That's how live tutorials work. It's good to see a few familiar faces coming back. That's wonderful. You've had the summer off, and you're raring to go, ready for some more physics. So I'm really impressed, really happy with that. I had a message come through from a friend and from a colleague who said that in their son's school they are not doing separate sciences at the moment. In year 10 it's just a science teacher who is delivering all three of the sciences, and of course I won't name any names because that would be unfair and probably unprofessional, but the rumour is that the biology teacher is very reluctant to teach physics, and that's a real shame if that's the situation. Luckily you've still got me here every Saturday for at least half an hour to go through some physics with you. Now I teach primarily AQA, and I've taught AQA for a long time, but I have also taught the EdXL IGCSE and the Cambridge IGCSE in the past, so I'm familiar with those schemes of work as well. If you're doing a different scheme of work, perhaps you're doing the EdXL GCSE or maybe OCR or one of the other boards, the lesser known boards, then do let me know with a bit of notice so I can have a look online, look at the specs and make sure that I cover things that are appropriate for you as well. Hopefully I'm coming through loud and clear. What I thought I would do, because it's the first session of the new term, I thought we would start from the very beginning, the most fundamentals, the basics. And we'll go through some things, ask you some questions. If you're watching this and you think, oh, this is easy, I know all this. Oh, hello, Lex. Sorry, I've just had a message come through from Lex. If you're thinking, oh, yes, I know all this is all stuff I know, then that's really good. It's always worth revisiting things and revising things, any knowledge, to make sure it's firmly in your head. But if there is anything as we go through it that you think, this is easy, I've done this before, actually that's a good thing, and stick with it, because you never know what you might gain from it, but actually just doing it again will help you learn it more thoroughly, and you need to have this sort of knowledge and understanding ready for your exams. If exams happen, you need to have this knowledge and understanding really firm. There shouldn't be any doubt about the things that you could be asked questions about. But if we do cover things and you think, actually I don't know that, you might want to make a little scribble, maybe get some notes, a notebook, keep yourself organised, some paper, a pen, make a few little notes as we go through it. Of course I'm never going to look at them, but it's to help you get your thoughts in order. And then you can always ask me, or if you have teachers at school, if you're home educated, then that doesn't really apply, but if you've got teachers at school you can ask your teachers, and if there's anything you're still not sure of, and you can always bring back questions to me. So what I thought we'd start with today is energy, because you really can't get far in physics without the concept of energy. I mean, in many ways, physics is just the study of energy and forces. That's what it's all about, in all sorts of different contexts. So I'm going to tell you a very brief story which I heard from Richard Feynman. Unfortunately I didn't hear it firsthand. I was watching many of his old lectures. You can see them on YouTube. Richard Feynman, if you don't know, was a famous physicist. He was one of, I think, the best physics teachers there ever was. From the United States, very thick, I think it was a Brooklyn accent, very distinctive voice, but his style of teaching was really good. And when teaching energy, he taught it a little bit like this. He said, imagine you have a child that you're tasked with looking after and entertaining, but you're a busy person, so you don't really want to spend a lot of time with this child, so you put them in a room and you give them 10 building blocks to play with, and you go away for 8 hours and you come back. So how many building blocks do you expect to find in that room? And of course the answer would be you'd expect there to be 10 building blocks still in that room. And let's say that you do this, and the next day you're tasked with looking after the same child, so you give them the same 10 building blocks, you walk away, you come back, there's still 10 blocks. But one day when you come back, there's only 9 blocks. And you get very confused because you're absolutely convinced there should be 10 blocks. So you start looking for the missing block. And maybe you find it in a sand pit in the corner of the room. They've been playing with some sand pits and there was a block buried there. Well, at least you found the block, and now you know next time if you're a block missing, you can always check in the sand pit. So you go away, you come back, you look how many blocks there are, and there are 10. You go away, you come back, there are 9 and 1 in the sand pit. You go away, you come back, and there are 8 and 1 in the sand pit. You think, oh no, we're missing another block. So you start hunting around the room and you notice there's a sink in the corner of the room. And the water level, you swear it wasn't as high as it was yesterday, now it seems higher. So you think maybe there's a block in that sink, but I can't get in the sink to see if there's a building block in it. But you suspect there might be. So you go away, you come back and you find 9 blocks, 1 in the sand pit, and the water level of the sink's gone down again. And you start writing this down and you measure the volume of a block and you work out the volume of water and you convince yourself, yes, there are still 10 blocks, but sometimes one's in a sand pit, one's in the sink. So you go out of the room, you come back in again, and you keep doing this. And one day you find there are 7 blocks. And you think there's 1 in the sink and 1 in the sand pit, but there's only 7 blocks. So you think, where's the other block? And then you notice the window is open. And you look out the window over at the floor, and there's a block on the floor in the street below. And you think, okay, there's another block down there, so I better make sure I shut the window when I count my blocks. And this goes on and on and on. And one day you notice there's 11 blocks, and you think, what on earth's going on here? And it turns out, you find out, there's actually another store of blocks in this room you didn't realise hidden under the bed, and so on. And the idea of this story is that these blocks represent energy, and we can hide them in different places. We can put them in the sink or in the sand pit or under the bed or out the window. We can lose them. And we can give them to the child, and we can put these blocks in different places. But the number of blocks, we're convinced, is always the same. The blocks represent energy, so we can bury energy in different places. And we call those things energy stores. Now, traditionally, energy was taught in 2 different ways. Either you learnt about energy types, different energy types, and energy can transform from one type to another, or you learnt about energy stores, and energy can be transferred from one store to another. And historically, it was more popular to teach energy types, and certainly that's what I was taught by my teachers. But the exam boards now prefer the language of energy stores. I mean, it doesn't actually matter, but you need to get used to this idea of energy stores. So when an examiner mentions an energy store, what they mean is a way that energy can be manifest, a way that you can collect those blocks together, a place you can hide those blocks. So what I want you to do in the chat is list as many energy stores as you can think of. And if you're thinking, I haven't got a clue what any of them are, remember that you might have been taught it as energy types lower down in the school. So maybe just list the energy types. So go ahead, pop into the YouTube chat now, and I'll read them out as they come through. And I'm going to give you just a couple of minutes, how many energy stores you can think of. It doesn't matter if you're wrong. It really doesn't matter. I'm not going to shout at you. You're allowed to make mistakes. That's how we learn. Those people who have tuned in before know that usually I wait 7 seconds. 7 seconds is roughly what the delay is between me saying something and you hearing it. So I usually give you a few minutes to write something, but then I count 7 Mississippis, so I know that the signal's been received your end. So I should expect to see some of these energy stores starting coming through now. Maybe you're all typing frantically. Don't make a list, just type one at a time so that they can start trickling in. You know, if you've written one and you're trying to think of another, just hit enter. Let me see what you've written. So 1 Mississippi, 2 Mississippi. Here we go. They're all starting to come through. So we've got kinetic, potential, static, Static electricity, I think that says. I know static, elastic energy, gravitational potential, thermal, elastic potential. This is great. I think we've basically got all the ones I care about already. I'm going to type these because I'm actually slightly faster at typing. So kinetic we had. Oh, well, I would be faster if I didn't make typos. Kinetic, potential, static. Some of these are right, some of these are wrong. Elastic. We've got kinetic already, then we've got potential we've got already. I might be reading the same list there. Kinetic, gravitation, come on, Keith, you can do this. Gravitational potential, we've got thermal, we've got elastic potential. Okay, so we'll stick with there, we've got a list. Oh, chemical, nice, well done, Freya. Chemical potential, I'm going to add the word potential in there, chemical potential. So, in this list, let's go through and give it some ticks. Kinetic energy is a store. It's a way that energy can be stored. A body that is moving has kinetic energy. Potential energy is a little bit too vague. It's a little bit too vague. So we'll take this off the list. A static energy, not quite. There is static electricity, but the word static just means not moving. And so we wouldn't talk about static energy. We wouldn't allow that. Elastic, again, that's a little bit vague. We tend to talk about elastic potential. So we've already got elastic potential on the list. I'll take out elastic. It's good, but it's not as good as elastic potential. Then we've got gravitational potential. Thermal energy, I'm very happy with. Yeah, and chemical potential, I'm very happy with. Electrical energy didn't get mentioned. I guess that's maybe what you meant by static, electrical energy. Or there's, I'll add this down here. And there are others that perhaps we're not going to add to this, other energy stores we're not going to add at this stage. For example, we might talk about nuclear potential energy or binding energy. We're not ready for that yet. That's going to come a little bit later. Maybe year 13 for some of it. So, okay, we've got a list of energy stores. Energy can be transferred from one store to another. And there's a technical name for the amount of energy that you transfer from one store to another. Do you know what that is? If you think you know, pop an answer. If you don't know, just type the word don't know, or not sure, or something, just so that I'm not just sitting here waiting, not sure if you'll get the message or not. So, do you know the technical name for the amount of energy that we transfer? 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Nope, Lex isn't sure. That's okay. Nope, Freya's not sure. Nope, Teddy's not sure either. That's okay. It's called work. Technical term, work. Or we could say the work done. So the work done is the amount of energy transferred from one store to another. And when we do work, we transfer energy. That's the language we use. Doing work means transferring energy, and the amount of work done is the amount of energy transferred. So, do you know the unit of energy? Unit of energy. And there are a few units, so I should be clear about this. The unit that we use in exams, the unit that we use in physics, the SI derived unit of energy. I don't want calories. So we've got here Teddy saying, what? That's a unit of power. It's related to energy, but it's not energy. Freya saying joules. Lex is saying what? Okay, so joules is correct. And I don't know if you realise this or not, Freya, but you actually wrote it correct with a lowercase j as well. Even though joules, named after James Prescott Joule, the joule as a name is a proper noun, the name of the unit is a common noun, so we don't use a capital J. However, the symbol we use for the unit does have a capital J. This is a convention we use for all units. In electricity, we've got the coulomb, we write it with a lowercase c, but the symbol, when we're writing the number, is a capital C. We write the name of the unit as a lowercase c. The watt, Oh, you didn't do that on purpose. Okay, but I mean, congratulations anyway. The only exception to this is if you are starting a sentence with it. So, for example, joules is the unit of energy. Then you'd start with a capital J because it's the start of a sentence. So that's the only exception to that. Anyway, so joules is the unit of energy. It is therefore also the unit of work done. Now, energy transfer diagrams. If you are doing an IGCSE, you may have to learn about Sankey diagrams. I think I'll have to check and see if the spec has changed, but the spec, both Cambridge and Excel for physics, used to have Sankey diagrams in them, and it probably still does. The spec for AQA GCSE physics doesn't have Sankey diagrams, so I'll start with just a normal energy transfer diagram. I will then describe Sankey diagrams, and if you're not studying it, you can either listen to it and learn because it's good, or you can put your fingers in your ears and ignore it. It's your choice. So let's start with energy transfer diagrams. Let's use the context of a ball being thrown in the air. So let's draw a little diagram. Here's my ball. It has been thrown, so I'm not touching it anymore, and the ball is moving upwards with some velocity which I'm going to call u. So it's moving upwards with velocity u. But it's not touching my hand anymore. And just to emphasize that, here's a picture of me and my hand not in contact with the ball. Okay, and that's basically a perfect picture of me. That is, I should be in an art exhibit or something. So this ball goes up in the air. What's the main store of energy at the moment? It's not very high up. We're going to catch it again when it arrives at the same height. So what's the main store of energy? It's got energy stored in it. What's it stored as while it's moving upwards? 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Gravitational potential energy is one answer. I'm not saying if it's right or not yet. Kinetic energy to gravitational potential energy. Not saying if it's right yet. Okay, so the main store at this stage here, where it's not very high up, and actually it's going to return to the same height. Yes, it does have some gravitational potential energy. I'm not interested in it because I'm going to throw the ball, it's going to go up in the air, then it's going to come back down again to the same height. So I'm not really changing the total amount of gravitational potential energy there. So the main energy here while it's moving is kinetic energy. So we could write down kinetic energy. And actually this raises an interesting question. Where is 0 gravitational potential energy? 0 joules. Where does the ball have to be for it to be 0? I'm afraid we're not going to answer that question until year 13. And the answer may surprise you. I'll tell you the answer now just because it confounds people, but please don't get worried about it. The only position where the gravitational potential energy is 0 is infinitely far away from all mass. But you'll do that when you study gravitational fields in A-level physics. So for now, please don't worry about that. Let's say that the initial height here, let's call this height 0, and then as we gain in height, that's our height there, h, then we start with 0 gravitational potential energy. I know it's not true, but that's 0 compared to that height there. And as we gain height, we lose kinetic energy. So the way we show that is by showing the kinetic energy store being passed to the gravitational potential energy store. I've gone off the side of my screen there, so I'm going to abbreviate this to GPE. Gravitational potential energy. Okay. Now the amount of energy that's been transferred across is called the work. What is doing the transfer? There is something physically happening. Why does the energy know to move from the kinetic energy store to the GPE? You know, from the block is in the sink to the block is under the bed. How does the energy know to move across? What's actually happening in terms of the physics to move that energy? Any ideas? And if you don't have a clue, if you're thinking, I don't know, it just happens, I really don't know, then just say, I don't know. But you might have an idea of what's happening. What is picking up those blocks from one place and moving them to another? Any ideas? The mass decelerates? Yes, it does. And then changes direction? It will do, absolutely. So what is causing the mass to decelerate? How does the mass know to decelerate? What is happening to this mass to make it decelerate? Not sure, don't know, that's okay. Gravity, absolutely right. Okay, let's make it more general. What is gravity? And I'm after a Key Stage 4 answer. What is gravity? There's some wonderful answers to this question if you ask PhD students who are studying astrophysics or cosmology. I'm not after that. At GCSE level, what is gravity? Just after one word. Got 5 letters in it. A force. A force. Perfect. So we can say forces do work. And this is absolutely fundamental. And this, unfortunately, if you're learning physics from a non-physicist, very often this gets forgotten. The reason why it gets forgotten is because there is a tendency for young people, unfortunately, to get energy and forces mixed up sometimes. It's true. They'll say kinetic energy, and then they'll start talking about gravity energy, and they think, no, you mean gravitational potential energy, and they'll start talking about friction energy, and you say, no, that's a force, and they get confused. And so far, none of you have got confused with that, so that's really good. But forces are what do the, Forces are what do the transfer from one energy store to another. So whenever work is done, there is a force involved. And we can actually show this on this diagram by writing gravity here. Now, some physics teachers are going to get very fussy about this and say, no, gravity is not a force, you should say gravitational force, and they are correct, but no one cares. Your examiner doesn't care. So let's pick our battles. If you want to call gravity a force, you go ahead and call gravity a force. And I can tell you now that PhD cosmology students call gravity a force sometimes, so why not? If it's good enough for them, it's good enough for you. So kinetic energy, gravity transfers that to gravitational potential energy. What happens next? And I might have to scroll a little bit sideways for this. Fortunately, I can do that. So what happens next? It's not the end of the story. One Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Kinetic, yeah, absolutely right. The GPE does increase, but that's what's represented here. That's what we're trying to show on this diagram, is we've gone from kinetic energy, we've moved that energy to gravitational potential energy. So what I've showed by this arrow is there's no kinetic energy left at this stage here. It's now all I don't know if you can see this yellow arrow. It's all gravitational potential energy now. So what happens next is it's transferred back into kinetic energy. It's transferred back into kinetic energy, and what we can say here is a force that's doing the transfer, and the force is you're all so interactive today. I'm really enjoying this. There's 3 of you joining in. It is really making me happy. Gravity, absolutely right. Gravity is the force. So gravity is a force. Right, then what happens? Okay, remember the person catches the ball. So I actually don't have a ball in here with me I have got, however, an air freshener that can act as a little prop for a ball. So the person threw the ball in the air, it went up, it slowed down, it stopped. It's got no kinetic energy now, it's all gravitational potential energy. It falls, gravity's making it fall, it's getting faster and faster, so it's gaining kinetic energy, and then it touches the hand, and then where's the kinetic energy go? Where's it gone? What's happened? Kinetic energy, where's it gone? We haven't finished the story yet. Any ideas? Transferred to hand, but into what store? You're correct, the hand has the energy, but in what store? I mean, we could say kinetic energy in ball, gravitational potential energy in ball, kinetic energy in ball, and I think we all agree that the last step, the energy is going to be in the hand, although actually some of it will still be in the ball, but in what form? It won't be gravitational potential energy because it's gone down and it's now back at that original height. So all the gravitational potential energy we gained when it climbed, we've lost again when it fell. So where's the energy gone? Now this is going to be difficult for you to accept. So I want you to imagine a bouncy ball and a hard surface, a table. And the bouncy ball bounces on the table. In a way, it's still kinetic energy, Teddy. In a way, it is. So as the ball bounces, it slows down, stops bouncing. But where's the motion gone? And the way Feynman described it, again, I do love the way he describes things. When the object was falling, everything was moving in the same direction. So we had this nice regular motion. And yeah, the molecules were vibrating a bit, but in general, there was this prevailing motion downwards, an organised motion downwards. And we can think of that as the kinetic energy of the ball. But then the ball hit the floor, and eventually it stops moving. That motion hasn't gone, it's still there. But instead of this nice organised motion, we've now got very disorganised motion. The atoms that make up the ball and the surface have gained motion, but it's all random. They're all moving a bit faster than they were before, but in random directions. So when we increase the speed of, or just generally increase the motion of atoms within a substance, we heat it up. That's what thermal energy is this movement of the particles within a system, or the atoms within a substance. Everything's moving a bit faster, and I think that's a really nice way of visualizing it. That nice regular motion has gone, and now we've got very irregular motion that you can't see because the atoms themselves, each atom itself, has gained that motion. So the question then is, and this is in, I better fill this in, thermal energy in ball and hand. But the question would be, what force is doing that last step? What force is transferring the kinetic energy into thermal energy? Is taking some nice regular motion and making it irregular. Any ideas? And if you don't know, if you haven't got a clue, just say you haven't got a clue. But listen, you can guess. You don't know each other. You're never going to see each other again. It doesn't matter. It's just names on the screen. Just guess. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. No answers coming through yet. I wonder if that's because you're either typing answers or maybe the video's lagged a little bit and you're a few extra seconds behind me now. That's possible. There's no answers. Not sure. The force that says that you won't fall through the ground in the earth. It is. That's exactly what it does. It's also the first force you ever learn about. And you learn about this force in primary school. And I can see none of you are quite sure. Maybe you're reluctant because you think it sounds a little bit too obvious or a little bit too infantile as an answer. Yeah, it is. Well done. Teddy's got it right. Push. Push force. Your hand pushes the ball up. As your hand is pushing the ball up, the ball which is moving down slows down and stops. So, ball's moving down, you're pushing it back up with your hand when you catch it. That's what you do. If you don't believe me, throw a ball in the air and catch it, and you'll feel that the ball pushes your hand down a bit. That's because you're pushing the ball up. And that push force, that contact force, is what's taking that nice regular motion, which we understand is stored in the kinetic energy of the ball, and making it thermal energy, or transferring it to the thermal energy store, very irregular motion. I mean, that sort of diagram there That is groundbreaking. When that was first suggested by James Prescott Joule, papers are written about it. This changed the world. It's the reason why the unit of energy is the joule. This is such a revolutionary idea. A few hundred years old now, many hundred years old, but it's still a revolutionary idea. Okay, so let's just quickly cover Sankey diagrams then. So if you're if you're doing AQA physics in particular, because I've got the most experience with them, I know Sankey diagrams aren't on the course. I think they're still on the course for the IGCSEs. So if you're studying, you're a home student, home educator student, you're probably going to be entered for an IGCSE, so this is relevant to you. If you are younger, you're not yet doing GCSE, it's worth paying attention because this is often taught in Key Stage 3 anyway, because it's good physics to know. And also, you never know what's going to happen in the future, and all of a sudden your school might choose to do IGCSE. So it's worth paying attention anyway. So let's draw a Sankey diagram. A Sankey diagram is a slightly better way of representing this energy transfer diagram, because within the diagram is information about what, or how much, I should say, how much energy is being transferred. This thing I've written here is quite a simplification. There's air resistance. And so because there's air resistance, not all of the kinetic energy will become gravitational potential energy, and not all of the gravitational potential energy will become kinetic energy again. As the ball moves through the air, it's bashing into the air molecules, and so we're losing some of that regular motion to the irregular motion of the air molecules. We know what that means. The air heats up. And so we should have added arrows coming off here, extra arrows, showing that we're increasing the thermal energy store within the air. And we could do that on this second part here as well. So on a Sankey diagram, I'm going to have to try and add that in. Actually, the gravitational potential energy wouldn't be transferred. It's only when the object's moving that air resistance is acting. So it would be here, wouldn't it? Thermal, my handwriting. And let's put in air here. And I'm just going to finish this off before I can't leave it. And let's add this as air resistance, sometimes called drag. That is some small writing. Air resistance, sometimes called drag. Okay, so that's a bit better as a diagram. So let us draw it as a Sankey diagram, so we can see the actual proportions. And I'm just going to do that first stage. Let's say 4 squares represents my initial amount of energy. Oh, I've done that arrow a bit big. Let's say 4 squares represents my initial amount of energy. Okay? 4 squares. Can you see the squares on your screen? Do you mind just commenting and let me know if you can see the squares on your screen? Because I'm not quite sure if it's clear enough when it's being transmitted through the internet. I can see squares on my screen, and I can see this is 4 squares wide. Yes, good, okay. So the width of this arrow, 4 squares, represents an amount of energy. Let's just pick a number. Let's say it represents 100 joules of energy. And what we can do is we can label this arrow, and sometimes it's labelled before the arrow, sometimes it's labelled on the arrow. I can label this arrow kinetic energy. So here we have kinetic energy. We've got 100 joules of that. And in a perfect world, we'd have all that kinetic energy transferred to gravitational potential energy. And the width of the arrow on the other side is still 4 squares, and therefore is still 100 joules, still 4 squares. But that's not actually what happens. What actually happens is we have some air resistance, and therefore not all of these 100 joules make it to the other side. So on your diagram, I'm just going to delete some of this. On your diagram, you've got to show that, let's say that 75% of the energy makes it to gravitational potential energy. I've just plucked a figure out of the air. So let's draw that to there, to there. Okay, so if this is 75% of the energy has reached this final stage, that's 3 squares wide or tall. How much energy is that in joules? What does this represent, this width of arrow? What does it represent? 75 joules, perfect. So 75 joules of energy. So 25 joules of energy has gone missing. And so what we do is we can either draw that as an arrow coming off at right angles, or we can draw it curved. And often we draw these things as curved. Sorry, it goes that way on the screen, doesn't it? Often we draw these things as curved arrows because it looks nicer, but actually that makes it far more difficult to draw. So I'm going to start with some nice right-angled arrows. And I'm going to draw this nice right-angled arrow here. The size of the arrowhead doesn't matter. No one cares about the size of the arrowhead. That's a slightly wonky arrowhead as well, but it just doesn't matter. It's because I've got snap to grid turned on, which in OneNote means sometimes it snaps to grid. I didn't design the software. Okay, so the width of this arrow is 1 square wide. How much energy is represented? Ah, you're a little bit behind, are you? Okay, well this will be recorded, so you'll be able to watch it back, don't worry. So this over here is our thermal energy. And yep, we've all got that. That's 25 joules. And so that would be a Sankey diagram showing the kinetic energy of the ball. Only 75% of it is transferred to the gravitational potential energy of the ball, and 25% of that energy is transferred to the thermal energy store of the ball. And you can see clearly what's going on with these arrows. In fact, I could draw this arrow carrying on a little bit further back if you wanted, to make it a little bit easier to really visualize what's going on. This bit at the bottom here has been sort of peeled off. And sometimes we draw this with a curve instead of an angle, but it's easier to draw with an angle, so there's nothing wrong with that. When I described this to my students back when I used to teach this, I described it as being like cheese strings. I don't know if you've ever had cheese strings. I don't eat them anymore. For reasons that I won't pontificate now, pontificate about now. But anyway, cheese strings, if you're not familiar with them, they're some sort of processed horrible goo which is put into a cylinder, and you're able to peel off bits of this cylinder, and that's their main selling point. That and the fact that they're salty and fatty, and children like food they're not really supposed to eat. So if you imagine this is a column of cheese string and you've peeled a bit off, that's quite a nice way to visualize it. When the ball finally hits the hand, do you have 100 joules of thermal energy or just 50 joules? It's a very good question. If I carried this on, I would have the 75 joules of potential energy, then splitting, because actually that would all go into kinetic energy, sorry. So we'd have the arrow carry on from gravitational potential energy to kinetic energy, then a bit more would split off for thermal energy, and it might be 25 joules that splits off, but it probably won't be, because it's not going to be going as fast the second time. So it's going to be a little bit less splits off the second time, and if you want, I can draw that. Should we do this? So let's carry this arrow on. We've got gravitational potential energy. I can make the screen smaller a bit later. And I'm sorry for the fact it doesn't quite join up, but I think this is okay. Now this is going to transfer to kinetic energy, but not all kinetic energy. Some of the energy is going to come off as thermal energy. And it's probably not going to be as much as last time, because we won't be travelling as fast, because we've already lost some of the kinetic energy. So this is going to be tricky to draw now. Let me have a look clearly. What proportion do you think that is? About 2/3? I think that's about 2/3. I might need to get my calculator out in a bit. So let's go up. And we've lost 2/3 of this arrow, so we've got a third left, so that's about there-ish. And that will carry on. And so if I stopped there, like this, okay. Let's label these. That one there. You don't have to draw these labels, by the way. These things I'm drawing in blue, because you've used square paper and it's all to scale, you actually don't have to do this. So if 1 square is 25 joules, I think I'm going to get my calculator out. What's 2/3 of that? So what is this arrow that comes off as thermal? This here is kinetic energy here, but then a bit comes off as roughly 17 joules. Yeah, I'd say that's a pretty good estimate. So we've got 17 joules coming in here. And down here we've got thermal energy. And this is thermal energy in the air, remember? So we could even label this in the air. Thermal energy in the air, thermal energy in the air. And what is left to be the thermal energy that goes into the thermal energy that goes into the hand. So you can work this out. What I'm asking is, what's the width of this arrow here? $58, yeah, pretty good. This is 58 joules of energy here. And actually, where's that going to end up? That's going to end up as thermal energy in the hand and ball. So, hand and ball. It's gone behind the screen, so let's just move across a little bit more. Okay, so I'm going to zoom out, or as I say in lessons, I'm going to de-bigger this so you can see the whole thing in one go. I'll make it a little bit bigger. Okay, think that should all be visible. Should be able to make that out. So there would be a pretty typical Sankey diagram for throwing the ball in the air and then catching the ball, and where's the energy going. And you can see what we've got happening. The arrow gets narrower each time something gets sort of tapped off. Thermal energy going into the air, but that only happens when the ball is moving through the air, which is why all of the gravitational potential energy gets converted to kinetic energy, but then some of that kinetic energy very quickly gets converted to thermal energy. And then what we're left with at the end, thermal energy, which is when we've lost all of our kinetic energy. And we could work out then how much hotter the ball gets and the hand gets and all the rest of it. If we were doing A-level physics, we might take it a step further. So that's a Sankey diagram. It's not just an invention for, so is the thermal energy just lost to the air, or is it recovered when the ball hits your hand? No, the thermal energy that's lost to the air dissipates. It's dissipated. The air moves all the time. Warmer air, through convection, rises up, and cooler air replaces it. So that energy is gone. You can never recover that again. That's the second law of thermodynamics, I think. The same is true of the energy at the end here. You can't really recover it, but at least it's all in one place. So if ever you could recover energy, thermal energy in one place, you might be able to do something with that. Okay, so I'm going to show you just very quickly some Sankey diagrams that you could find if you Googled it, Sankey diagrams, to show you that this isn't just a made-up thing for the sake of physics exams, just one more thing to learn. Sankey diagrams do appear all over the place, not just in the context of energy either, although usually in the context of energy, but not exclusively. So if we look here, we've got some beautiful Sankey diagrams, really complicated ones that show all sorts of lines going all over the place, and they all share one common feature, which is that the thickness of the line is proportional to the amount of whatever quantity the Sankey diagram is showing, the amount of that quantity that it represents. So you can use Sankey diagrams to show cash flow, but here's one: national budget. Money coming in, money coming out. Where's the money coming in? Where's the money going out? Again, you probably can't see this on the screen, it'll be a bit too small, but you get the idea. You get the idea that the Sankey diagram, where the thickness of the arrow is showing the proportionality of the amount of that quantity, in this case it's money, however let's pick a different example. This is workflow, so maybe that's time that's being spent in this particular diagram. This one here is energy that's being transferred from one side to the other. So Sankey diagrams as a general tool appear all over the place, but you do learn them in physics, especially with the IGCSE, in the context of energy transfer and work. And I think that's a convenient place to stop. What I haven't done yet is any real maths, the equations for kinetic energy, gravitational potential energy, and so on. And we can cover that next time when we look at conservation of energy and I'm happy to do that next time. We can also look at conservation of energy and efficiency next time. I think I'll put that as a plan. I'll pencil that in, unless anybody has anything else they want to go through, in which case let me know through Facebook Messenger. If you go into Facebook Messenger, drop me a message. I will get that message during the week, and then I can plan what I intend to do around that. No, you're very, very welcome. So a little thank you message come through. That's lovely. You don't have to thank me. I'll do it because it's fun. So drop me a message if you want me to go through anything else. Otherwise, my plan will be to go through energy. We should be able to get most of it done next week, but if not, maybe the week after. And then we'll just push through the course and do maybe some electricity after that, and maybe what we'd do after that, maybe nuclear physics or something. But what I intend to do is try and cover a bit of everything over the course of this term, maybe a few terms, basically this year. Should be possible actually to cover a whole GCSE in a year, I reckon. But just watching this isn't going to be enough. You would have to also do some work of your own, I'm afraid. And I can't recommend enough Isaac Physics. I'm not actually, well, I do get paid by them, but not for this. Isaac Physics is free for you to use, and it marks your questions for you. So if you took part in the summer school, you've already been using Isaac Physics, so you're familiar with how that works. And I'm happy to share with you some sheets that I've prepared for you to use Isaac Physics, for you to work through it. But in terms of services, you've also got Seneca, which I'm not going to say bad things about because I don't want to get sued by them. I don't rate it, to be honest with you. But a lot of people say Seneca is very good, so you can go ahead and use that. It's better than nothing. And what other services are there out there? I think they're the two main ones, to be honest with you, and of course interactive with me here. So between us, I think we'll all get the course done, which will be good. Right, anyway, I'm going to stop. Thank you very much for coming. It's been a really lovely morning, a lovely way to start the term. I'll see you next week. Stay safe, have fun in school if you're in school. If not, have fun with your homeschool, and I'll see you next week.